For this homework assignment, you are asked to do exercise 9.4a on page 289, as well as exercise 9.4b on page 295. Beginning with exercise 9.4a, you were instructed to identify whether each of the following statements below is a tautology, self-contradiction, or contingency by creating a truth table for the statement. For problem 2, you are given the following proposition: A or B or not A. And the way we construct the truth table is as follows. We create our two columns over here on the left for our two propositions. Our two atomic propositions, A and B. And then we lay out the truth values for those. And we know that we are going to, just like with all truth tables, first calculate, step one, calculate the number of rows. And the way we calculate the number of rows is we take the number 2 and we raise it to the power of however many distinct propositions atomic propositions we're going to have. So we're going to have 4 rows, and in the first column right here, we do half true, half false, and true, false, and then simply transfer those values out to the columns we have for the other occurrences of these atomic propositions. And then what we're going to do is we're going to fill in the truth values for all the connectives, starting with the connectives of least scope. And the first thing we need to do is identify what our main connective is. And our main connective here is this disjunction, or. And then we have two other connectives. This disjunction here, which applies to these two atomic propositions. We also have this connective, the not, but that applies only to this atomic proposition right here. So we're going to begin right here with filling in the truth values for the very first disjunction, and we're going to use A and B right here in order to determine it. And the truth values for this is just quite simply, we just follow the truth table for just a standard disjunction. So when A is true and B is true, this is going to be true, this is going to be true, this is going to be true, and then only when both disjuncts are false. That's the only time where a disjunction is false. So we fill that in pretty easily. Then we're going to come to the other proposition, or the other connective of least scope, which is going to be this negation here. And what we do to fill that in is we just take the opposite of the truth values that appear right here under A. So put a false here because this is true. Not true means false. Not false means true. And that's how we do that. And then finally, we're going to fill in the truth values for this disjunction here. And we use the truth values for this and this because the disjuncts for this disjunction up here, this is one disjunct, A or B is one disjunct, and not A is the other disjunct. And just like with all disjunctions, what we do is a disjunction is true only when both disjuncts are false. So we can look right here without even looking at this column and know that at least one of the disjuncts is true. So this is going to be true, 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 and we look right here and this disjunct is false, but this one's true, so this is going to be true. And so for this proposition, all of them, every instance of this proposition will be true, and this we call a tautology. So number 2 was a tautology. I'll go through the truth tables a little more quickly for the following examples. I just thought on the first one I'd kind of walk through it a little slowly. Alright, so for number 3, you were given the following proposition: A or B or A. A or B or A. And we're going to fill in our truth table for this one just as before. The only difference between this proposition and the previous one is that the previous one, this disjunct on the right hand side was not A. Here it's just A. And just like before, this disjunction, the second disjunction, is our main connective. So we're going to fill in our truth table just like before. Start with the first disjunction, and I'll just go ahead and skip to it. And then we arrive at these truth values, and then we look right here, and just like with all disjunctions, they're true as long as one disjunct is true. So this is going to be true, 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 and then lastly this is going to be false. And so here is our truth table. Now, in this proposition, some occurrences of it are going to be true and some are going to be false. And this we call a contingent statement, or it's a contingency. It's neither a tautology nor a self-contradiction. Number 5, D and not E. I'm sorry, if D and not E, then E. So what we want to do is we want to create a truth table, just like all the other truth tables. You see I have a column for all of our different connectives and our different atomic propositions. And then what we want to do is we want to start filling in this truth table by determining the truth values for the connectives, beginning with the connectives of least scope. Now, our main connective is this one right here. This conditional is our main connective. Then we have two others, and we have not E. And hopefully at this point it's becoming very obvious to you that the not E applies only to this E, so this one is the connective of the least scope, and the and right here, this applies to both D and E, so we'll do that one after we do the not. So let's begin right here, and this is really simple matters, but not true means false, not false means true, not true is false, and not false is true. So we fill that column in very easily. Then we're going to move to the conjunction, and this is true only when both conjuncts are true. So here we have true and false, so it's going to be false, true and true. That's the only occurrence of true here. False and false will be false, and then false and true will be false. All right, and then finally we come to our conditional. And remember, a conditional is true, is false only if the antecedent is true and the consequent is false. Every other occurrence of a conditional ends up being true. So here we have our antecedent is false. Well, anytime you have a false antecedent with the conditional, it doesn't even matter what comes next. It's going to be true. We have a true antecedent and a false consequent, and that is going to be false. That's the only time it's false. False and false. We don't even have to look over here because this one right here, we have a true antecedent and a false consequent. That's the only time that it's false. So this is going to be true, and this is going to be true. And so here is our final truth value for this proposition. We determined that it's true sometimes and false other times, and just like the previous example, this is also a contingency. All right, and this is, I believe, our last one on this exercise. So if A then B or not B. This is only going to have 4 rows because we only have 2 distinct atomic propositions, so we'll just go ahead and fill in our chart right here. And we need to determine what connective. Step 2, we got to figure out the truth value for our connectives, and we need to determine what is our main connective, and it is going to be this disjunction right here. You see the parentheses right here, they restrict the scope of the conditional. This conditional only applies to A and B. We also have not here, but that only applies, a negation only applies to the B, whereas the disjunction applies to this entire proposition is one disjunct, and this entire proposition is the other disjunct. So we could start anywhere, or we could start in a couple of different places for trying to figure out the value of the connectives, but I'm going to start right here with this connective just because it comes first and we could easily begin there. We could have started over here with the not, but it doesn't really matter logically speaking. And just like with all conditionals, the only time this is false is when the antecedent is true and the consequent is false. So this is going to be true, false, true, true. And then we come over here, and we're going to do the negation, and the negation we just take the opposite. So not true is false, not false is true, not true, false, and then not false is true. All right? And then finally, we come to the disjunction. And remember, this is true as long as one of the disjuncts is true. So again, if A, then B is one disjunct, the other disjunct is not B. So here we have true and false. Well, that's going to be true. False and true. It's going to be true. True and false. It's going to be true and true and true. True and true. It's going to be true. And so you see here that all rows are true, and for that reason this is also a tautology. Now I don't think I gave you guys a self-contradiction, but maybe the reason I didn't is because the examples in the book were just, they had too many atomic propositions or too much going on, and I didn't feel like making you guys fill in a chart that had a billion rows in it. But anyways, so that's how we determine properties of individual propositions. Now on page 295, exercise 9.4b, you're dealing with figuring out relationships between two propositions. And here you would determine whether these statements in each of the following sets are equivalent, contradictory, consistent, or inconsistent by creating truth tables. So for the first problem number 2, you're dealing with two different compound propositions. Here we have not A and B, and we also have not A, or not B. There's a lot going on in that second one. And what we have to do is we have to fill out truth tables for both of these, and then we're going to compare them. And so here's the truth table for the first one. These I'm going to blow through a little more quickly than in the previous set of exercises. But I've already filled this in. And you can look down here if you want, but here's the truth table for it. Now, the truth table is basically the same truth table for any disjunction. That's just what we have right here. And then we're just taking the opposite of that. We're saying not A and B, so just fill that in. And we have here is the truth table for not A and B. False, true, 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 true. Then we do one for this proposition over here, which is not A or not B. And I've gone ahead and taken the liberty of filling that one in as well. And here's what it looks like. And as you can see here, what we are dealing with is, in the first row, the first proposition is false and this one's true. And in rows 2 through 4, this first proposition is true, whereas over here this proposition is false. And so we call these two propositions, they are a contradiction, or they are contradictory. You can contradictory or contradiction, either way, you can say it either way, it doesn't matter. This is not a self-contradiction. Only an individual proposition can be self-contradictory because, again, it's contradicting itself. Here we have proposition number 1 contradicting proposition number 2, so we just call it a contradiction. So both of these statements cannot be true at the same time. And actually, if one statement, I should be a little more clear, if one statement is true, the other is false. If one is false, the other is true. So this is actually very reminiscent of our lesson on categorical propositions when we talked about the square of opposition and contradiction. If you recall, contradiction formed the X from the top left to the bottom right and from the top right to the bottom left. And if one statement was false, the other was true. And if one was true, the other is false. For instance, all S or P was contradictory of some S are not P, if you recall that. Those statements contradict one another, meaning if one is true, the other is false, and vice versa. Same thing here. All right. Number 3, not A and B and A or B. So just go ahead and fill out these charts. And this one is the exact same as the previous chart that you saw on the other page. And then we have A or B, which looks like this. And we look at this and we notice some similarities here. For this one, and we notice some differences as well. So in the first row, this one is false and this one's true. But notice right here in rows 2 and 3, these propositions are both true. Now they do have the opposite values, and I should have drawn this differently. I should have put like maybe a not equal sign in between here and a not equal sign right here. Maybe that would have looked better. But notice that rows 1 and 4 are different, but rows 2 and 3 are the exact same. And what this means is that at least some of the time, or at least one row, in fact 2 rows, these propositions can both be true. And so we call these propositions consistent. They're not equivalent because their rows aren't identical, and nor are they contradictory because they're not completely opposite. But at least sometimes, in fact, you only need one row where they can both be true in order to be consistent, and these propositions are. Number 5, if C then D and not C and not D. So the first proposition is just simply the truth table that we have for conditional, so that's not terribly complicated. And then this truth table over here, it involves a couple more steps, but here's the final result of it. And you notice for this one, the row 1, they have the same truth value. Row 2, they have the same truth value. Same thing for 3 and 4. And for that reason, these propositions are equivalent. They have the exact same truth values. And this is kind of interesting when you stop and think about it, because I told you guys a long time ago that all of the connectives can be rewritten and using different connectives. So here we have the conditional if C then D. Well, here's another way of writing it, not C and not D. These have the exact same truth values. Kind of interesting stuff, I think. In fact, I guess what this shows, go back a slide, is that if you were developing your own logical system, or some logic systems actually do this, they just dispense with some of the connectives. Like basically you could dispense with or, you could dispense with if and only if, you could dispense with the conditional and just use negation and conjunction. You could do everything in terms of negation and conjunction. So for whatever that's worth. Some logics do that, in fact. Alright, so here we have if C then D and C and not D. And here's the same truth table you saw in the previous one. I don't know why I put parentheses around this. You didn't need it, but because you weren't dealing with any other connectives. And then we have also this proposition over here, C and not D. And here's what this truth table looks like. And you might have guessed, go back a slide, if these two propositions, if C then D, and not C and not D are equivalent, the only difference here is you're actually, in the previous example you were saying not C and not D, where here you're saying C and not D. So you're affirming that's true, so this is going to have the complete opposite truth value of the previous example. Anyway, long story short, these two propositions are contradictory. You can see that, you might have guessed it from the fact that in the previous example you were negating this entire proposition. Now you're not. So if the previous side example they were equivalent when you were negating, now you're affirming, you're not negating. It stands to reason these are going to be contradictory, and that's exactly what's going on here. This one's true, this one's false, this one's false, this one's true. So these propositions, not only can they not be true at the same time, if one is true, the other is false. For that reason, they're contradictory. Number 15. Now, this one, there's a lot going on here, but the truth is it's no more complicated than anything you've seen thus far. It's just more steps involved. That's the thing about truth tables is, once you understand how to do them, they're actually all the same and pretty easy. They're just very, very tedious. And what becomes most difficult is just making sure that you actually write T's where they're supposed to go and F's where they don't, because your eyes will like skip lines. It's not that it's logically difficult or in any kind of way abstract reasoning is required. It's just when you get in a habit of going T, T, F, 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 sometimes your eyes will skip lines or something like that. That's the most difficult part, not getting your eyes crossed. But with this one, we fill out our truth tables for the two propositions, and here the truth table for the first proposition is the exact same that you should have learned when you learned the truth table for the biconditional. The truth table for the second proposition is a little more complicated, and the key here for doing this one is just figuring out what your main connective is. And you can just, I'll slow down a little bit here, but you see that it's not going to be either of these conditionals because both of those occur inside of parentheses. And you can see the parentheses here, so it can't be those. It's not going to be the and, because look at the brackets here. That's restricting the scope, right, of the conjunction. What is left? The negation, and that occurs or has ranges over this entire compound proposition. So here's the truth table for it, and as you can see here, these two propositions have the exact opposite truth values, just like the previous example did. And so these two propositions are in fact contradictory. So we've looked at a number of examples, and hopefully you get a sense of how to do this. I know we didn't have examples to cover all the various propositions, or let me rephrase that, properties or relationships between propositions. On your upcoming exam, there will be ones that do cover, self-contradiction, which we didn't have an example just because the examples in the book I thought were too tedious for you guys to have to write out. One on your test won't be quite that bad. I don't want anybody having to write out like 64 lines. That's just silly. But hopefully you get a sense of how this works. And the big thing I want you to take away from this is that these compound propositions, you can use different connectives basically to say the same thing. You can, and hopefully you even had an intuitive sense of this, that sometimes you can say things using not and or you can say things using not and, just depending on where you place those connectives. But like always, if you're having any trouble with this, please feel free to shoot me an email and we can square away any problems that you might be having.